Okay, thanks. So this is an overview of our work in VLSI routing that we are doing for 30 years or even more. So you see a very incomplete list of co-authors that also reflects the fact that we are working on this for a long time, and I show you some glimpses of this work. So when we design chips, there are two classical steps: placement and routing. So first, in placement, we have to place the objects. Here there are 8 million rectangular objects that altogether contain 1 billion of transistors. Some of the larger rectangles you can see, some of the smaller ones you cannot see. And you want to place them in a way that the pins of these rectangles are somehow nearby, close together, because those you have to connect in the second step, namely in routing. And this talk is about routing. So we have here about 30 million pins on this telecommunication chip that we designed a few years ago. And we have to connect the pins of one net. So the set of pins is partitioned into nets. And the pins of each net needs to be connected by a Steiner tree. And we can do that on a couple of routing layers. Here we had 9 routing layers. Today we have sometimes 20 routing layers. And we have to design these three-dimensional Steiner trees. So here, just to give you an impression, we have 1 kilometer of wire length on a thumbnail. So these are some nice numbers and some nice pictures. Pictures of this kind, by the way, you can see more in the arithmetic. This is a very detailed view of 1 millionth, roughly, of the chip, where you see essentially 2 layers. The green lines are power rails, and the red ones on the top layer here, mostly going vertical. And then the layer below has blue wires, mostly going horizontal. That's the way we pack the wires efficiently, by using one layer mostly horizontal, then the next layer mostly vertical, and so on. We cannot go diagonal, by the way. And the nice thing is, if you look at the same chip after manufacturing, it looks exactly the same. So that's the output of our algorithm, and that's the output of the fab in the end. So that's nice. Theory and practice somehow coincide. And but let's now go more into mathematics. So how can we formalize the task? So we are given a number of routing planes, a set of nets. Each net is a set of pins. We can also say terminals that have maybe a set of shapes, or you can consider them just as points. And we also have some blockages, some space that we cannot use. And then we have rules that tell us when 2 shapes are connected and when they are sufficiently separated. And we need to compute a feasible routing. So connect the shapes of each net, and the shapes of different nets must be separate from each other. That's the simplest version of the problem. Well, then in addition, we have also some things like timing constraints that have become more and more important. The timing behavior of a chip, so the signals should really be fast. We should avoid long detours, and also the upper layers are much faster, have lower resistance than the lower layers. So for long distance, we should use those, and such things come into play, which makes the problem, of course, even harder. Now, is this a discrete or is it a continuous problem? Well, you can think of, as I formulated, it's maybe a continuous problem even, because we can choose any Steiner tree. Typically, we have some discrete grid that we work on. So since we're talking about continuous approaches for discrete problems, let's say it's a discrete problem. Good, so a very simplified view then is that we have a large graph with terminal sets, and we want to find vertex joint Steiner trees in that graph. Then, of course, it's NP-hard. Even simple special cases are NP-hard, and we really have huge instances to solve. So what do we do? So typically, there is this task is separated into 2 or 3 stages. First, we do what we call a global routing. We simplify the instance, make it much smaller, condense it in a sense. I will give a picture in a minute. And then it turns out we can still do global optimization. I will explain you how we can do it. Then, of course, with the global routing, we will ignore all the local constraints. So in the end, we can't ignore them. So we will work out the details in what we call detailed routing. I will talk about this later in this talk also. And then maybe in the end, we have to fix some very ugly constraints that we didn't care about in the previous process. Okay, once again, the graphs are huge. Even in the global routing, in the condensed graph, we still have 1 billion vertices. So this is not a small problem. But okay, so here's another picture how it could look like. We have in light green a global routing corridor, so maybe the output of the global routing, and then the detailed routing has to find the detailed wires in that corridor, which somehow simplifies and restricts the problem of the detailed routing task. So the classical way to do global routing is you take your chip area, partition it by a grid, here shown in black, into rectangular tiles. And then you say each tile is one vertex. You have, of course, for every plane a tile. You have a number of tiles on top of each other. And then you have a 3-dimensional grid graph. And you just map all the pins that are in one tile to that vertex corresponding to that tile. And you have to define then edge capacities. If you go from, or maybe I have a laser pointer, if you go from this tile here to that tile, you can put a number of wires. Maybe you can put 20 or 30 wires there. So you would put a capacity of 20. And usually you would not put a capacity in the other way, because on that red layer, we would prefer to go vertical. Then if you want to go horizontal, you should change the layer. You have some vias connecting these pins. Okay, and then it's packing Steiner trees, but now subject to edge capacity. So what have we gained here? We will see that actually this problem can be solved pretty well. And the model which we use to solve this, we call it or it has been called min-max resource sharing. And that's a very abstract model. And the advantage is that it allows us for including many more constraints that I haven't talked about yet. So here's the abstract model. We have a finite set of resources. Think of, for example, the edges of our global routing graph. They have limited capacity. And a set of customers. These are the nets. They want a solution. Every customer needs a solution. And so for each customer, we have a set of visible solutions that would be the Steiner trees for that net, but we haven't got them explicitly, of course. We will not list the Steiner trees. We have access to those by an oracle function that optimizes linear functions. So given a price vector on the resources, so every resource has a current price, then we can find a solution that minimizes the total cost, or at least approximately minimizes the total cost. I mean, the Steiner tree problem itself is NP-hard, but we can find a sigma approximation that we call a sigma, that we call a sigma approximate oracle by that we can optimize that linear function approximately. We can find approximate Steiner trees, for example. And the task is then to find a solution for each customer that, what we say, minimizes the congestion, minimize the use of any resource. So BCR would be what the solution for customer C uses from resource R, the percentage of the available amount that that resource has, say. And you want this actually to be at most 1, then you satisfy all the constraints. Or we can just say we minimize the maximum. That is a different way of doing it. Okay, that's of course a difficult problem. It still contains disjoint paths and so on. We use continuous approaches to solve discrete problems here. So we take the convex hull of the solution sets. And that's the min-max resource sharing problem. And so now once again, to apply this here in global routing, the resources could be the edges of the global routing graph, but also it could be like something like total power consumption, which you want to bound for your chip. You just define an extra resource. It's very easy. You can even optimize the manufacturing yield. I will not get into this. And we can optimize timing by defining resources for the edges of the timing propagation graph. I will get to this in a minute and explain it in a bit more detail. And then every net is a customer. It needs a routing solution. So the oracle must produce a routing solution, essentially a Steiner tree. Maybe we can choose the wire width also, and some that can come into play. And then we look for a solution of congestion at most 1. In the end, of course, we need an integer solution. We need one solution, not a convex combination of Steiner trees, but one Steiner tree. So we do the simplest possible thing, just randomized rounding a la Rakavan-Thompson. And that works pretty well. And at few places, you can even explain why it works well. And at very few places, it might not work so well. You do some local fix-up. So how do we solve that fractional problem? Essentially, it is a multiplicative weight update method. So if we first do a binary search to determine the optimum, we do some scaling to ensure that the optimum is around 1, which in practice, actually, we don't have to do really, because we know it usually for our instances. Then we maintain resource price. Initially, every resource has price 1. And then in every iteration, we call the oracle for every single customer. And after every oracle call, you would update the prices. And now you have this width reduction technique that is well known. So if the oracle tells you to use more of a resource than is available, then you use that output of the oracle call only to some extent and call the oracle again after the price update. So that's the thing. And you can prove that you get this running time, which is near linear. You see it is a near linear dependence on the number of customers plus the number of resources. You only have some logarithmic and some term, and of course the error parameter comes into play. So we can get arbitrarily close to the approximation guarantee of the oracle here with this algorithm. And that works surprisingly well in practice. And there are some speed ups that we can get. For example, by parallelization, we can do the oracle calls for the customers in parallel, and we don't lose any theoretical guarantee from this. We can avoid actually most oracle calls because we see that the previous solution is still good. We can identify this and then avoid the oracle call altogether. 80% of the oracle calls can be avoided by this. And actually, in practice, the number of iterations that we need to get to 1 or 2% to optimality is really small. So it's essentially we call for every customer. In the end, we call the oracle maybe 5 times or so, not much more. So that's why it is really fast. And it works much better than the theory tells you already. It's quite good, but it works even better in practice. And there were some questions. So in previous talks, when I presented this, I asked some questions. For example, it seems that it does not just optimize the worst resource, but even sometimes one resource is hopeless. You cannot do anything about it, but still you want a good result for the rest, of course. Does this algorithm do it? Another question is, you typically in the chip design process apply your routing algorithms many times and the input changes a little bit, but you still have the result from the previous run. Can you use, for example, the prices, the dual prices? Can you do a warm start? And do we need this binary search? That sounds a bit strange in practice. We will not need it anyway, but do we need it really in theory? And then my student, Daniel Blankenburg, who wrote his master thesis recently, he actually managed to answer all these questions. This is actually literally from a previous talk that I gave. Now all these questions are answered. Binary search is not necessary. You can avoid that. You can get rid of this log-log term, get the best possible runtime. Now, and actually, he also proved this runtime is best possible regardless of the price update mechanism. You can do whatever you want with your prices. Also, a warm start will not help you at all. You need this number of oracle calls in the worst case. And also, you get some result on the second best resource and so on. So this is some nice progress on this. Now, one word on saying how to model these timing constraints, because it's not completely obvious how to do it. So you have an acyclic digraph that models your timing constraint. You have the arrival times at the sources, at the inputs, required arrival times at the outputs. And then, so look at maybe this example is a very simple, is a path with 3 edges, right? So you have arrival time here, you have a required arrival time here, and then you have 3 nets. And of course, depending on how you route these nets, you will have a certain delay from V1 to V2. You don't know yet the arrival time here, so that you can compute. But you have an earliest possible arrival time here if this net N1 is fastest possible, and the latest possible if the other 2 nets are fastest possible. So it should be somewhere in between. And now what we define is a resource for time that has this time from the arrival time of V1 up to the latest of V2. And similarly for the other edges. And now if I choose the arrival time of V2 here, then I would consume, because I choose it a bit earlier than the latest possible time, I would consume of this resource, and only the rest is available for the delay of the net. And for the next edge, I would consume this amount because I'm here actually much later than the earliest possible time. So this is already used. And these would now be additional customers. Now, not only the nets are customers, but these are also customers, and it fits perfectly into this resource sharing framework. And that works. You can make it work in theory. You can prove that you can get near optimal solution with this framework. Maybe I skipped some of the details here. And also in practice, we use it all the time. So that really works very nicely. Let me not read this long slide. Here's some results in practice. So here is just what you do if you don't care about timing. You have a very good routing result. This is what we call a congestion plot. Everything is green, so you really don't use more of the edge capacities than you have. But this is the slack histogram. This shows you the timing result, and everything which is red is really comes too late, right? This is you have negative slack. You violate your timing constraints. Now, if you optimize every net for timing, the timing is good, but the routing is horrible. This is what they used in industry. They use some heuristics. The timing is okay, but they have some hotspots in routing where it will be very difficult to close. And this is how our algorithm automatically balances between the two and nicely converges in very few iterations. And you see the rounding in this case, it even improved a little bit in the end. So there was still some discrete element in the global routing. Namely, we defined these global routing tiles and we contracted them to one vertex. So we forgot about everything that happens in these tiles. We forgot about a lot actually. So it can be almost half of the total wiring that is inside the tiles that we now completely ignored. And that of course simplifies the model and makes it quite inaccurate and is not so nice. So here's a new approach to global routing, which we called continuous global routing. And so it fits very nice into this workshop. The solution to this problem is to rotate the tiles by 45 degrees. So here now we have rhomboidal tiles. So this would be one tile that is red, that has pretty high price at the moment, for example. This has a bit lower price, green is very low. And here you have some pins, and now you connect the pins at their exact positions. You don't forget where they are. And you want to find routes here in this plane. So it's a continuous problem. And the nice thing is, if you look at the wire here in this graph, so you would pay the price of the color where the wire lies. And now if you move a wire, let's say a horizontal wire, you move it north, then your total cost of that wire would change continuously, right? That is due to this rhomboidal structure. So it's a nice continuous problem that doesn't forget about the pin positions. But of course, how do we solve this really? How do we find Steiner trees? Now here, this looks like a bit difficult problem, but actually one can make it discrete again. So I go back to discrete. So by defining a graph, if you look at the red pin, for example, you can define all the horizontal and vertical line that goes through this pin, and then you reflect it at the tile borders, and you get this red grid. And you do the same for all the other pins, for the green, for the blue, and for the orange. And that gives you a grid graph. And Nikolai Henle, Pietro Saccardi, and Stefan Rabenstein have shown that this graph actually always contains an optimum Steiner tree for any set of prices, even in the three-dimensional setting with VR costs and everything. So that's so in the end, this continuous problem is again solved by a discrete as a discrete graph problem. So here are some pictures how it works in practice. So initially, every net wants to use the uppermost plane, which is very good, but you see the worst congestion there. And you see over the number of iterations, the algorithm improves more and more and gets rid of most of the congestion. And now it has a feasible solution in the end, in very few iterations. Now let's spend a few minutes still on the detailed routing part. Once we have this global routing solution, what do we do? So we really have to find detailed wires now. So that means the main task is actually to find a path, to have two components, S and T, that could be two pins of a net or one pin and already routed component that connects some of the pins. And we want to connect them in the subgraph G prime that still contains or models the space that is still available, because much of the space is used already by other nets. We do this sequentially. Of course, we do it in parallel. Many nets are routed in parallel, but essentially one after the other. And of course, we use many speed-up techniques. Parallelization, I mentioned, we restrict to the global routing area. That restricts the graph a lot, of course. We use highly optimized data structures. I will not get into it. And of course, we use the goal-oriented Dijkstra technique that is well known. So instead of using the actual costs, we use reduced costs by some feasible potential. And that, if you use that to be a good lower bound on the distance to the target, then this speeds up the Dijkstra algorithm. You label much fewer nodes. So the question is, what would be a good estimate to the target? That leads, of course, to non-negative reduced costs also. And one idea is just forget about the small blockages or so. Forget about G prime. Let's just work as G. G can be considered to contain everything. It's like a continuous problem. You can route everywhere. So we use, again, continuous techniques. We use the distances in G. We have different costs on different layers, maybe even in different regions, but we try to compute this distance. Of course, this must be extremely fast because we need to compute it at every single node that we label in Dijkstra's algorithm. So these are, of course, billions and billions of nodes. So the problem that we need to solve is, now for any given point, lay S1, we have a set of targets, a target set, let's say the green set here, with some axis parallel rectangles. What is the nearest target? What is the shortest path to a target? And now here in this graph G instead of G prime, so we forget about the local blockages. So we can route anywhere, but we have to pay a cost. For example, in the lower layer, it might be expensive to go vertical. Therefore, we would take a via up to the upper plane, take here the vertical wire and go down. That could be a shortest path. And if the cost depends only on the layer and the direction, then we can do that in O of L time for every target. So where L is the number of layers, L square is easy, but you can do it actually in linear time. And if the cost depends also on the tiles, which is very useful and allows you to model many things I will not have time to get into, then you should do some pre-processing. And you can then, after some pre-processing, you can still query it in essentially the optimal time, because I mean, you need to find out in which tile you are and on which layer you are, essentially. So you need log P plus Q plus L. And if epsilon is a constant, then this is optimal. You have some pre-processing time that we managed to get down so that it is really also efficient in practice. There was a previous version that was too inefficient to be used, except in some exceptional cases. So with this, we really reduced the number of labels in the Dijkstra. If you don't use that goal-oriented at all, you have this number of labels. If you choose just the L1 distance, the most easy thing you would come up with, you reduce already by almost a factor 2. But then with a simple model, we reduce further, and with a general model, still a bit. And we get down that this is the total running time now here on all these connections on several chips. Of course, these are done in parallel on 64 threads. So in the real world, you have to divide it at least by 64. And then these are many, including some very large instances. So some results that are already a few years old, but today they would look even better, that compare the overall router to some industrial tool. So you see there's an industrial router that uses for this test bed 9 hours and has a total wire length, here in this case of 16 meters and 11 million vias. And so our router used only 1 hour and 17 minutes on the same test bed, where we still had at that time a 3-4 hour post-processing that does some cleanup of some rules that we didn't care about. But even in total, it is, oh no, so that's the total time, even 2 hours and 45 minutes or so cleanup. And you see the overall result is we save 10% of the wire length, which is really a lot. So that's even if you save 1%, they would already be very happy. Here we save 10%, which is huge, and more than 20% of the vias, and also the number of detours. So a scenic net, 25% would be a net that is more than 25% longer than an optimum Steiner tree. And so we decrease those by errors. Yeah, errors. So errors are the remaining design rule violations. So we have a huge, you get a book of rules that is 500 pages or so, and nobody would read that, right? So in the end, you will have some remaining errors that simply nobody has implemented. And that means that some designers manually will correct these 222 errors, yeah? So they will spend a few days and correct those manually in the very end. Yeah, so this is basically the story. It was used for many chips, even the top processors, including the world's fastest computer, which you can also see in the RMM. And by the way, I should repeat, everybody who is here at HIM, show your HIM badge at the RMM entrance. You would get free entrance, and it's worthwhile going. Thanks.